Alright, so we'll start off with finishing up section 2.2. Not much left, and then we'll look at 2.3. So the last thing we need to look at in 2.2 involves using the calculator and finding an intersection. I think we've done it before, but let's practice it again. And to practice it, we're going to look at this example. So the example we're going to look at is about a company that makes a certain product. I think they make t-shirts, and they have fixed costs and variable costs. So an example of a fixed cost might be like the rent they have to pay to use the building. Doesn't matter how many t-shirts they make. The rent is the same every month. Okay, rent never changes. Or maybe if an employee works on salary, they make $50,000 a year. Doesn't matter how many shirts are made, that's their pay. That's fixed, it never changes. A variable cost would be a cost that they have to pay for every shirt. So maybe the material they use, right? They have to pay for each t-shirt that they make. It costs them a certain amount of money to make it. And that cost changes. They make 10 shirts or 1,000,000 shirts, it's a different cost. So this particular company has fixed cost of $200,000, so that never changes. And it costs them $1.50 for every shirt they produce. So they have to pay $1.50, maybe that's like if they're silk screening it or whatever it is. That's the cost to make each shirt. And then they sell it for $4. Now, remember, that's not all profit. Okay, so there's a difference between the revenue, which is just the money that they take in, and then how much of that money is actually profit. All right, we could figure that out, but not yet. All right, so what they want us to do is find a graph of two different equations. So first thing we got to do is come up with equations. But they want us to find a graph of an equation for the cost, and then an equation for the revenue. Right, so in terms of a variable here, what would the variable, what do we need a variable for that we don't know? Yeah?
How much do you need to cover the cost?
Yeah, so the cost will be a variable, and what is going to control the cost that can change here? How many
shirts were sold?
Right, how many shirts that we've sold. So I'm going to set up two equations. One for cost and one for revenue. So let's start with the revenue equation, because that one's a little easier. What's the money that the company charges per t-shirt? $4. And let's say we'll use X. I just picked X as the variable. So how would we represent the revenue if they sell X shirts at $4 a shirt? How about Greta?
The revenue is 4 minus 1.5, so 2.5.
Well, revenue, we're not going to worry about profit yet. So I see what you're doing with subtracting, but don't worry about subtracting yet. Revenue, just how much money do they take in altogether?
4x.
Yeah, perfect. So 4x. So that's their revenue. Again, not all of the revenue is the profit because they had a cost in making the t-shirt. So now let's figure out the costs. Well, we've got two costs. Fixed cost and a variable cost. Let's start with the variable cost. How would we represent the cost of making the shirts? Forgetting about the fixed cost for now. What would be my expression? Yeah?
Negative 1.5.
1.5, what?
Negative 1.5.
Well, remember, you can't really have negative cost. Cost might represent you losing money, but you don't lose negative money. Does that make sense?
Yeah.
You're still going to be positive money that you lose. So it's going to be a positive 1.5, and what would we have to put with that? 1.5, yeah.
X.
1.5x. Now, if we subtract it from the 4, then we could figure out the profit. But for now, we'll just figure out the cost. So it's 1.5x. But how would we account for the fixed cost with that? 1.5x, but
Adds 200,000.
yeah, we just add 200,000, but that's not times x. Because we don't pay 200,000 every shirt we make. We just pay 200,000 once. Okay, so there's our formula for cost and revenue, and now they want me to graph it. In my cost equation, I've got a y-intercept way up at 200,000. So we got to think about setting the y-max pretty high. Okay, x is how many shirts we make. Well, I know we're not going to make negative shirts. That doesn't make sense. And let's say we make up to, I don't know, let's just say 300,000 shirts. Okay, what I'm trying to see is where the cost and the revenue cross. If I can't see that on the screen, I'll adjust it and look further to the right. Are we going to have negative cost or negative revenue? No. Doesn't make sense to have negative costs. Your costs are still positive. And then the y-max, well, it's going to be at 200,000 for this top equation, but then the slope goes up from there, so it's going to go even higher. So why don't we try like 350,000? Okay, I'm just guessing with the x-max and y-max. We'll see how it looks. Okay, did I type the equations in?
I don't think you did.
No, it's really good. You got to type those in. So,
That's probably going to be necessary.
but we got a good window ready to go. So now, type the equations in. And there we go. There's our costs. There's our revenue. Yeah, it's okay. We probably went a little further to the right than I needed to. Maybe I didn't need to go as far as 300,000. I might have been able to even just go like 200,000, but 300,000 looked fine. It kind of squished it a little bit, but that looks good. So I would say that's a good complete graph, right? Because we can see where they cross. If the intersection point is off the screen, that's no good. Okay, no good. So here's your window. I wish I could grab it. It didn't put that box there. That was 0 to 200,000 and 0 to 350. That's all we had to do for that part. Just find a complete graph. Any questions on that? Okay, now we're going to do something with that graph, and we're going to find what's called the break-even point. So basically, the break-even point is when the cost and the revenue are the same. After the break-even point, now every shirt you sell beyond that, now you're making profit. Before the break-even point, you're still in the hole. You're still negative. Okay. So I kind of already showed you this graphically, but if you want to find when the cost and the revenue are the same, what would you be looking for on that graph? Yeah, you'd be looking for the intersection point. That's all. Okay, so if you graph the cost and revenue, where is the break-even point? It's the intersection. All right. So let's find the break-even point. Let's figure out how many shirts that the company would have to sell to break even. And we'll do it two ways. One way I'll do it with algebra. The other way I'll do it with graphing calculator. So break-even point. Cost equals revenue. Okay, that's the break-even point. Cost and revenue are the same. Okay. So algebraically, what that means is this. Cost equals revenue. Let's just look up what our formulas were on the other page for cost and revenue. I know revenue was 4x. What was the cost again? How much did it cost them to make the t-shirt?
1.5x.
1.5x.
Plus 200,000.
Plus 200,000. So if we wanted to solve this for x, subtract the 1.5, so now we're subtracting it, okay? Because now we're actually figuring out how many shirts we sold. So if you subtract 1.5 from 4, you get 2.5. And then divide each side by 2.5. Okay, let's see what we get. 200,000 divided by 2.5 gives me 80,000 shirts. So, if the company sells exactly 80,000 shirts, they won't have made money, they won't have lost money, they'll break even. Any questions how we solved it with algebra? Okay, let's do the same thing on the calculator. So for this part, I'm just going to show a picture. There's not really any work other than that. Does anyone remember how I get to the intersection? Like how I find it? Yeah.
Second trace.
So second, press trace. Yep.
Then 5.
And then 5 for intersect. And now pick a point somewhere on the blue graph. Doesn't matter where. Pick a point somewhere on the red graph. I'm just moving it down so you can see that I'm on it. And now it's because they only cross once, the guess doesn't matter. Okay. So if I do that, there's your intersection point, 80,000 shirts. So at this point, if you made 80,000 shirts, your costs would be $320,000 and your revenue would be $320,000. So your profit, if you take your revenue minus your costs, would be 0. That's it. That was the end of section 2.2. So any questions on that? Okay, so that part pretty straightforward. Great. So we'll spend the rest of today looking at section 2.3, which is on solving quadratic and linear equations with algebra. So we won't do as much with the graphing calculator for the rest of today. We pretty much just saw everything we're really going to use it for. All right, so go over a couple basic things first that I think you probably know from like Algebra 1, but just reviewing it. As I go through something, if you already know it and you don't feel you need to write it down, then it's up to you. So first of all, what is an equation? So we're going to be solving equations. Equation is just any time you put an equal sign between two expressions. There's an expression in math, 2x plus 5. There's another expression, 3x. Throw an equal sign between them. Now you have an equation. If the equation uses x as the variable, like I did here, we just say that we have an equation in x. That's just a fancy way of saying an equation where x is the letter. So when we're asked to solve an equation, solve usually means you're finding a number. Okay, you're going to get an answer, and it's like x equals 6. Okay, you're going to figure out what you're looking for. So it's a value that would make the equation true. So if I had something like 2x equals 12, we're looking for 2 times what gives me 12? 6. So x is the value that makes it true. Now, some equations are true all of the time. Okay, this equation is not. There's only one number you can plug in to make it true. But some equations, like the one I'm going to show you right here, you can plug in any number to make it true. Let me just pick a number like 1. If I plug 1 in, watch what happens. 3 times 1 is 3. 3 plus 2 is 5. So I get 5 on the left. 1 plus 1 is 2. 2 times 3 is 6. 6 take away 1 is 5. So I showed you that 1 works. You can plug in any number that you can think of, and it will always work. And if you have an equation that is true for all values, that's called an identity. And the easy way to see why this is always true is if you, what would you do on the right-hand side? And if you do this, it might make it a little more obvious that this is an identity. Yep.
You would distribute the 3.
Yep. If you distribute the 3, you get 3x plus 3 minus 1, but then 3 minus 1 gives me 2. I have exactly the same thing on the left and on the right. 3x plus 2. Whenever that happens, it's an identity. Versus an equation like this one is not always true. It could be true if you pick the right value for x. That's called a conditional equation. There's a condition that makes it true, and the condition here is that you let x equal 5. Any questions on those two types of equations? Identity, conditional equation. There's also the opposite of an identity, which is called a contradiction. It's an equation that's impossible to make true. No matter what you pick, you can never find a number that works. If you know these two, that's good enough. All right, so if they ask you to verify that a number is a solution, that means take the number they gave you, or if you found it yourself, take that number, plug it back into the equation, and see if you get a true statement. So to verify a number is a solution, take it, plug it in, see if you get a true statement. This would be one that's kind of hard to solve with algebra because it's a cubic. If that was an exponent of 2, we could do it because we have the quadratic formula. And we can factor. Make it an exponent of 3, it's not so easy. So I'm telling you, or I'm suggesting that negative 2 is a solution. I want you to double check that it is. Okay, so just double check negative 2 is a solution. Okay. If negative 2 is a solution, when I plug it in on the left-hand side, what number am I hoping to get? I'm hoping to get 0. If I plug it in and get 0, because that's what's on the right, then I'm good. Let's check. So we get negative 2 cubed. Sometimes people make a mistake when they plug in there. It's minus 2 plus 6. I'll put a question mark because I don't know if it equals 0. I hope it does. If it doesn't, then one of two things. I either did something wrong when I checked it, or negative 2 isn't a solution. How about Rebecca? What's negative 2 cubed? Careful, positive or negative? Negative, yep. And then Kylie, minus 2
Plus 2.
turns into plus 2. Now, negative 8 plus 2 gives me negative 6. Negative 6 plus 6, I get 0. Okay. So we just confirmed negative 2 is a solution. I'm not saying it's the only solution. There could be more, but that is a solution. Any questions on that? Okay. So, let's look at this. So that's an example of a linear equation. It's kind of like y equals mx plus b, except I didn't use the letter m, I used a. So any linear equation, eventually when you're solving it, can be reduced to something that looks like that. Even the one that we're about to do, which doesn't look like that right now, it looks like it's much more complicated. Eventually, I can make it look just like that if I want to. So the only thing we got to be careful about is what A and B are. So what this says is A and B are real numbers. A and B are elements of the real numbers, meaning A and B can be positives, negatives, fractions, or decimals. The only thing A can't be is 0. Because if you make A 0, what's 0 times anything? 0. So if you make A 0, what you've just done is you wiped out x. Now you have a constant equation. Okay? If it doesn't have an x, it's not considered a linear equation. It's a constant equation. All right. So A and B can be anything you want except A can't be 0. Okay, so let's solve that and see what we get. So Emily, what would be my first step? And I might have to do this property a couple times on the.
Distribute the 2 and the 3.
Yeah, distribute the 2. And you said also to distribute
The 3.
the 3. So 4x minus 6 plus 3x plus 3. And for now, we'll just leave the right-hand side. Isabel, what would be my next step?
Combine all terms.
Yep. And what would be your like terms on the left-hand side?
4x and 3x and negative 6 and 1.
Yep. 4x and 3x. That gives me 7x. And positives are negative 6. Positive 3 gives me a negative 3. All right. Now I got to get all my x's on the same side. All right, how would I get all my x's on the same side? Yeah.
You can subtract 5 from both sides.
Subtract
The 5x from both sides.
5x. Yep. So we could subtract 5x. And if we want, at the same time, we can add 3. So that's going to cancel the 3's. That's going to cancel the 5x's. And now I've got 2x equals 5. And now if you're like, well, that doesn't look exactly like what he said it should look like, I could make it equal to 0 if I wanted to. Wouldn't really help me solve it, but I could write this. And now it looks exactly the way I said a linear equation looks. Something times x plus a number equals 0. Something times x minus a number equals 0. Same thing. Again, getting it equal to 0, though, doesn't really help you with a linear equation. We do that with quadratics. At this step, the easiest thing is just divide by 2. And you're done. X is 5x. Okay, any questions on solving a linear equation? In Algebra 1, we spend probably a whole week or 2 before we even get to something this complicated, but at this point, you guys should be good with distributive property and combined like terms, all that stuff. All right, so let's look at solving an absolute value equation. Kind of like what we just did, but we have to solve 2 equations. So the first step when you're solving an absolute value equation is to make sure the absolute value expression is isolated, okay, is by itself. What do I mean by that? Well, when you're solving an absolute value problem, you're going to have something like this. That's an example of an absolute value problem where the absolute value is by itself. There's nothing on the left-hand side outside the bars. Here's an example where the absolute value is not by itself. First thing I would have to do here is minus 6 from both sides. Okay? Or if I had something like 4 times the absolute value, I would have to divide each side by 4. Okay? So you want to get this whole section alone first. In a lot of problems, it already will be. So after the absolute value is by itself, then we're going to split it into 2 separate problems. And the reason we're splitting it is this is how you get rid of the bars. Okay, you can't start minusing 2 or dividing by 3 until you get rid of the bars. So the first equation, well, pretty much it's exactly the same equation that you started with, except you just get rid of the bars. So you're going to copy down the same equation and just erase the 2 bars that are there. That's the first one. The second one, you're going to do the same thing, copy down the original equation. You're going to erase the bars, but there's one extra step. You're going to take the number that's on the other side, in this case it's a 2, and you're going to make it the opposite. Okay? You're going to change the sign of it. So if it's negative, you make it positive. If it's positive, you make it negative. And that's it. Those are the 2 steps to solving absolute value. Again, in Algebra 1, another thing I would spend a whole day on, just solving absolute value equations. We'll do one example or so, and hopefully that'll kind of refresh it a little bit if you don't remember how to do it. Any questions on the 2 steps? So 2 equations. One of them you just take out the bars. The other one you take the bars out and make the number on the other side the opposite. Okay. So our problem is the absolute value of 2x plus 3 equals 5. So Emily, if I look at that problem, is the absolute value by itself? Yeah, there's nothing else on the outside. Just bars, that's it. No numbers like that or anything. Okay. All right, so now we're ready to split it into 2 problems. Okay, I'll do the first one and then I'll ask someone for the second one. First one, copy down the same problem. Just take out the bars. We have to come back and solve that in a second. Let's set up the other equation first. Anyone think they can give me the other equation that I'm going to have to solve? Yep.
It's the same thing as what you just wrote, except instead of 5, it's -5.
Yep. So now we solve each equation. We put the word "and" between it. That's how our book does it, because we're going to say x equals this and x equals this. 2 different values. So -3 from each side. 2x equals 2. But we get x equals 1. And what's nice is when you solve these equations, it's the same steps. We minus the 3 and then divide by 2. We can do the same thing on the other side. Minus the 3, divide by 2. So -5 minus 3 gives me -8. Divide by 2. And I get x equals -4. That's it. That's how you solve an absolute value equation. Any questions on that? Okay. So mixture problem. Okay, let's take a look at that. So before we get into, I think the next thing is going to be quadratics. But before we get into that, we're going to look at a kind of an application for linear equations. Okay, not quadratics, just linear. And that's a mixture problem. When we do mixture problems, we're going to have to set up 2 equations. Okay, one equation, well, let me give you an example. Usually you're going to be taking 2 chemicals and mixing them together. Right? So you have like sometimes you buy rubbing alcohol and it says on the bottle like what percent it is. Sometimes it's like 80%, sometimes it's 90%. So let's say I said to you, all right, I'm going to give you a bottle of 80% rubbing alcohol and 90%. I want you to mix them together so that you create an 83% solution. So I want you to make 83%, and I want to have 10 gallons of it. So my question is going to be, how much of each one do you need to mix? So one equation is going to have to do with the total amount. So I don't know what I said, 10 gallons or something? So one of the equation has to do with how much stuff you want, and the other equation has to do with the concentration you want. So I said like, I don't know, like 83%, something like that. So these are the two equations you have to set up. The first one is pretty simple. Amount 1 and amount 2 are going to be variables, usually x and y. So you usually have something like x plus y equals how much stuff do they want you to have when you mix it up. And then the second equation is a concentration one. They're going to tell you the concentrations as a percent. But you have to make sure you always use decimals. So 83% would be 0.83. So decimal, decimal, decimal. All decimals for your concentration. Okay, so let's look at a problem. It's going to be exactly like what I just told you. Two different percentages. You're going to mix them together. And we'll go from there. Okay, does everyone have those two equations? Okay, so those are kind of like your template. All you got to do is fill in basically x and y for amount 1 and 2. That never changes. But the concentration will change. Depends on the problem. Okay, so we have two solutions. One that's a 10%, one that's a 25%. I want to mix these two together so that when I'm done, I have 15 liters, and I want it to be a 12% solution. So just using kind of common sense, which solution are we going to need more of? A or B? Yeah, more of A, because the final concentration is a little stronger than A. It's 12% instead of 10, but not that much. So I'm going to use mostly A and a little bit of B. But I want to know exactly how much. So I said you can use X and Y. For this problem, I might just use A and B to represent amount 1 and 2. Because the solutions are already labeled as A and B, so that'll keep things simple. All right, so let's start with our equation for the total amount. Let's let A represent how much of solution A we're going to use, and let's let B represent how much we need for solution B. So what did it say in the problem? When we add those up, we want how much? 15 liters, yep. So I'm going to take how much I use of the first solution, plus how much of the second, and I want it to add to 15. If that's all they gave me, that's not enough information to solve it. Because I could use 1 and 14, or 2 and 13, or 12 and a half and 2 and a half. With that, there's an infinite amount of answers. But this is the part that's going to narrow down one answer. All right, so we're going to have concentration times an amount plus the second concentration times the second amount, final concentration, final amount. So let's start with, this will be for A, B, final. Okay, so concentration. What's the concentration of solution A? Yeah.
10%.
10%, and as a decimal?
0.1.
0.1, yep. Put 0.10, but if you put 0.1, it's the same thing. So concentration times how much of solution A are we using? We don't know. We're using A. So solution A, solution B, and then the last one is the final solution. Okay, what's the concentration of solution B? Yeah, 0.25. And how much of that solution are we using? B, we don't know. Okay, now the final solution. Final solution, the concentration is 12%. And the final amount, 15 liters. Now the right-hand side is always going to be a number in this equation that you can do. So let's just do that. 0.12 times 15, that gives me 1.8. All right, so now the only problem is I have two equations. I have two variables. I got to get this down to an equation with one variable. So does anyone remember what it's called? You can do something with the top equation and then plug it into the bottom. There's a name for it.
I don't know the name, but can't you like put a variable on that side and then plug that in for the variable on there because there's only one variable?
So you want to get a variable alone right here?
Yeah, and then
Exactly, yep.
plug that into the...
And you could pick, it doesn't matter. Which variable do you want to get by itself?
A.
A. All right. So I'm just going to put an arrow over here. So how would you get A by itself?
Subtract B from both sides.
Yep. Subtract B from both sides. Now you've got a formula for A. It's 15 minus B. And what did you say to do with the 15 minus B, Sam?
Plug that in to A.
Yep. Substitution. Okay, so that's what that's called. We're going to substitute in for A, and when I'm done, I'm only going to have an equation with a single letter. Okay. So 0.1 times A, but now we know A is 15 minus B. Copy everything else down exactly the way it was. If you just want to put 0.25b, you don't really need parentheses. We know that means multiply. So now this equation isn't even as bad as the first one that we did, because you only have to do a distributive property in one spot. So let's multiply that out. 0.1 times 15 is 1.5 minus 1.5b plus, 0.1b. Don't listen to me. So 0.1 times 15 is 1.5, 0.1 times b, 0.1b. Plus 0.25b equals 1.8. Combine our like terms. What's negative 0.1 plus 0.25? 0.15. So 1.5 plus 0.15b equals 1.8. How about Carolyn? What would I do next?
Subtract the 1.5 from both sides.
Yep. Subtract the 1.5. Sometimes with decimals we need a calculator, but these ones aren't too bad. So 1.8 minus 1.5 is 0.3. And my last step to get b by itself. Yeah.
Divide by 0.15.
Divide by 0.15. And what's 0.3 divided by 0.15? 2. So we need 2 liters of solution B. And how many liters of solution A would we need? Bless you. Shy?
13.
13. Because remember, it was a total of 15. And once you know one of them, then you automatically know the other one. So there it is. If you mix 2 liters of B and 13 liters of solution A, you'll get exactly what they were looking for. Every mixture problem is exactly like that. Just always start by setting up these two equations and then substitute into the longer one. Doesn't matter if you substitute in for A or for B. You could have done it either way. Okay, any questions on that one? Okay, so that's an application for linear equations. Okay, so now we're going to move on and look at quadratics. So quadratic equations look like that. A little more complicated because the highest exponent is now a 2. When you have a quadratic, those numbers in front, the a, b, and c, can be positives, negatives, fractions, or decimals. That's what this is saying right here. A, b, and c can be real numbers, except a can't be 0. If it was, you would have this. That's a 0. 0 times anything is 0. You just wiped that term out. What's left is what we just studied. That's linear. It's not quadratic. It's A, B, and C, anything you want except A can't be 0. Okay, what's one way you can solve a quadratic equation besides the quadratic formula? You can use this method if the numbers are nice. Remember, yeah? Factoring. Yep. So one way you can solve a quadratic is factoring. Now, the nice thing about the quadratic formula is it always works. Even on a problem that you can factor, you can still use quadratic formula. You can always use it. But if you gave me a problem that's factorable relatively easily, I could solve it faster with factoring and quadratic formula. All right, so let's see if we can factor. Well, I'm telling you, this one is factorable. So let's see if we can do it. Okay. Anytime you want to factor, first thing you got to write down is 2 sets of parentheses. Okay, so we always start with that. Now, this one isn't going to be bad to factor because if you look at the number in front of x squared, 2 is a prime number. If you look at the number at the end, 3 is a prime number. What that means is there's only one way you can multiply 2 numbers together that are integers and get 2. It's not like if you had a 12 in front. If you got a 12, we got all kinds of options. 6 times 2, 4 times 3, 1 times 12. Then it gets harder. But there's only one way we can get a 2. So, first thing you want to figure out is the term that's going to go here and here. Anyone think they can tell me those two? Yep.
One's going to be 2x and the other one will be x.
Yeah, 2x and x. Doesn't really matter at this point which one you put where. Now, next thing we look at is these signs. Okay? There's 4 different cases that could happen. Positive, negative, negative, positive, both negative, both positive. Depending on the case, it'll tell you what your signs need to be down below. So this time, the middle is positive, the end is negative. Anyone think they could tell me what my signs have to be in the parentheses? Yeah.
I say both negative.
Well, we've got to multiply a number here and a number here so that when I multiply them together, I get a negative answer. So if you're going to multiply 2 numbers together and get a negative, what would you have to have? A positive and a negative. Yeah, you got to have one of each. And I'm putting them in the order that she said. That might not work. We'll see. And now the last thing I need is 2 numbers that multiply together to give me 3. Well, 1 and 3. Could you do 3 and 1? You could. But you'd be wrong. So don't do 3 and 1. In this case, it's 1 and 3. So let's check it and see if it works. So you got 2x times x. That's good. 2x times negative 3 is negative 6x. 1 times x is plus 1x. That gives me negative 5x. Is that what I wanted? No, what did I want in the middle? Positive 5x. So we got the right number. You got the wrong sign. Switch the signs. Now 2x times 3 is 6x. Negative 1 times x is negative x. 6 take away 1, there's my 5. Perfect. So now we factored it. That's the hard part. Now, if you're going to multiply something times something, and you're going to get 0, because that's what the problem says. Something times something is 0. What does that mean? How can you multiply two things together and get 0 is the answer? Yeah. One of them or both of them have to come out to 0. It's the only way you can multiply two things together and get 0. So either this has to come out to 0 somehow, or this has to come out to 0. One or the other. So if we solve them, if you plug in a half, you get 2 times a half is 1. 1 take away 1 is 0. 0 times anything. Well, if you plug in a half, you get 3.5. But 0 times 3.5 gives me 0. If we solve the other one, get x equals -3. If we check it, -3 times plus 3 is 0. 0 times, this doesn't even matter, but 2 times -3 is -6. Minus 1 is -7. -7 times 0 is 0. Okay, so quadratic equations can have up to 2 answers for real numbers. Sometimes we have imaginary answers, but we're not going to get into that yet. Any question on that? All right, so if you can't solve it with factoring, or even if you can solve it with factoring, you can always use the quadratic formula. Okay. Does anybody remember what the quadratic formula is? Or if not, maybe just start with the letters that are in it. Just the 3 letters. There's 3 letters we use. But if you know the whole thing, go ahead.
Is it -b plus or minus the square root of b squared minus 4ac over 2a?
Perfect. Yeah, exactly.
Well done.
Yeah, nice. Some people don't remember it, but that's perfect. Some people have like a song they sing. Yeah, you got a song? Yeah, here you go. Whatever works. This part that Sam said, b squared minus 4ac, that special part has a name. It's called the discriminant. And that part basically controls whether or not you get real answers or imaginary. For this week, the part that I have circled will always come out positive. Because if it came out negative, then you'd be taking square root of a negative number. You can't do that with real numbers. And if you're not sure what the A, the B, and the C are, they come from right here. A, B, C. So the key is you've got to make sure your equation is equal to 0. If it's not, get it equal to 0 first. Okay? That's what I just told you. So they call that standard form. So make sure your equation is in standard form before you start. Okay, so let's try this one. What I usually do, you don't have to do this, but if it helps, you can do it. Just off to the side. Just write down what A, B, and C are. Now, what should I do first to this equation? So, especially because this is going to affect C. Should I?
Get the one with everything.
And how would you do that?
Subtract 1 from both sides.
Yep. Now I should be able to easily read off what A, B, and C are. Okay, so Haley, what's A in this case?
2.
2, and B?
2.
2. And this is important. If you said C is 1, that would mess us up. C is -1. Okay, now I'll plug it all into the formula Sam said and see what happens. So -b. I do a little bit of it as I go. I don't do a lot, but just a few things I do in my head. So -b plus or minus the square root of b squared. What's 2 squared? So 4 minus 4 times A times C all divided by 2a, 2 times 2, gives me 4. Now, looking under the root, I have 4 minus a positive times a positive times a negative. What's a positive times a positive times a negative? A negative. So you have 4 minus a negative number. So what's going to happen when you subtract a negative? It's going to turn into a positive. So I like to do that right away. So negative 2 plus or minus the square root of, let's do 4 times 2 times 1. Morgan, what's 4 times 2 times 1?
Yeah, 9.
Careful, you're not adding that 1. It's just 4 times 2 times positive 1. 8 plus 4. So we have 8 and now plus 4. 12. And now that's not quite as simple because we can break down the square root of 12. How does the square root of 12 simplify? About, yeah, go ahead.
Is it 2 to the square root of 3? 2 times the square root of 3?
2 times the square root of 3, yep. And now that we did that, that actually worked out nice because we have a 2 we can cancel from everywhere. If you want to cancel a number there, you've got to do it here, here, and there. Don't worry about what's under the root, that doesn't matter. It's just what's outside. So the final answer is negative, don't forget that, negative 1, plus or minus, there's 2 answers, square root of 3 divided by 2. Now, some people separate that into 2 fractions. You can write it this way. That's exactly the same thing. I usually just leave it as one big denominator. But if you want to write it like that, that's fine too. Any questions on that? All right. So let's finish up with this one. All right, so this is one where I think a picture is kind of helpful because just reading the wording is a little confusing. But basically, you've got a rectangular piece of cardboard, and you're going to cut squares out of each corner. Okay? Kind of like that. So you started with a rectangular piece of cardboard, and you cut a square out of each corner. Specifically, the squares that you cut are 5 inches by 5 inches out of each corner. So now what we're making here is we're going to make kind of a tray. We're going to fold the sides up on the dotted lines. So we're going to have a tray without a top on it, just the bottom and sides. Okay, W and L represent the width and the length of the original piece of paper, okay, before you cut it. So the width, I'm trying to show, goes from top to bottom, length, left to right. Of course, once you fold the sides up, then the actual length and width of the tray is going to be a little smaller. The width and the length of the original piece of cardboard. Okay, so that's what I just told you. The cardboard is being folded along dotted lines to make a box. And one fact that they're going to give me, and we'll need this, the length is twice the width. Okay? So for the original piece of paper, the length is double the width. And the volume, once you make it into a tray, obviously it's not the volume of a flat piece of paper, that wouldn't make sense. The volume of the stuff that would fit in the tray is 2,040 cubic inches. So, find the dimensions of the original piece of cardboard. Alright, so first thing we gotta figure out is what formula we should use. Well, there's a number in that problem that's gonna give you a hint as to what geometry formula you need to use. Anyone think they know what the formula is we're gonna use? Yes. Well, yeah. Yep, it has to do with volume, because that's one of the numbers in the problem. So everything in this is going to be based on the volume formula for a, does anyone remember what that shape is called? It's like kind of like a box. It's not a cube, because a cube would have all the same sides, but do you remember what it's called? Oh, what is it? It's a rectangular prism, exactly, yep. So I need to remember that formula. Does anyone remember what the formula is for volume of a rectangular prism? Yep. Perfect. Length times width times height. Now I just need to figure out what's the length, what's the width, what's the height, what's the volume. So there's 4 things I need to plug in. Well, I already have the volume. Volume is 2040. The length. So remember, this formula is for the volume of the tray. It's not the volume of the piece of paper. That doesn't even make sense because the paper is flat. So the length of my tray is right there. How much shorter is my tray than the original piece of cardboard? Shaq?
10 inches.
It's 10 inches shorter because you cut 5 off here and you cut 5 off here. So originally we had L and we cut off 10. So what's left right here? L minus the 10. So that's the length of my tray. L minus 10. Now the width of my tray. The width is right here. Originally we had W, but we cut 5 off and another 5 off. So what am I left with after I cut off the corners there? Well, Isaac? So we started with W, and I just want to know how long this is from there to there. Exactly, it's W minus 10. That's the width of the box. And now the height, what's the height of the tray that I'm making? Yeah. It'd be 5, because when you fold up the side, it's going to be 5 inches tall. So the height is 5. Now the only problem with that is we have 2 variables, but there's something we didn't use yet. The length is twice the width. So how would I write that as an equation? Length is twice width. Yeah.
2W equals L.
Exactly. L equals 2W. Now, what could I do with the 2W so that I only have one variable in the bottom? Yeah.
You would plug it into L.
Plug it in. Right there. Once I do that, all I'll have is a W. So 2040 equals 2W minus 10 times W minus 10. Now, there's a trick you can do here to make the numbers a little smaller. I'm going to show you what that is. If you don't mind big numbers, then just FOIL everything out the way it is. But 2W and 10 both have a 2 in common. So what you can do is that you can take a 2 out, leave everything else the same. And now I've got some like terms. 2 times W minus 5 times W minus 10 times 5. What's 2 times 5? 10. So I have 2040 equals 10 times w minus 5 times w minus 10. But now I can divide each side by 10. That goes away. That goes away. And it makes my numbers a little smaller. If you don't want to, you don't have to do that, but I'd rather deal with a number in the hundreds than in the thousands. Okay, so now let's FOIL out what's on the right-hand side. Okay, w times w. How about, Isabel, what's w times w? Yep. W, can you say it again?
W squared.
Yep, perfect. W squared. W times negative 10. How about Nick?
Times 10,
Negative 10w, and then we have another negative 5w, which gives me let's write it out. Let's do the first one. What's w times negative 10?
Negative 10w.
And then w times negative 5? Yep, and we'll come back to combining the like terms in a separate step. And then negative 5 times negative 10 is positive 50. So from here, it's just a quadratic equation. Okay. Get it equal to 0 and use either quadratic formula or factor. I don't think this is going to factor nicely. So w squared minus 10 minus 5 is minus 15. And then I've got to bring the 204 to the other side. So I'm going to do 50 minus 204. Okay, so negative 154. So let's plug it in and see what we get with the quadratic formula. We're definitely going to need a calculator because the numbers are kind of big. So we get negative b plus or minus the square root of, that part I can still do in my head, negative 15 squared is 225, minus 4 times a is just 1 in this case, times c, all over 2a. Kylie, what can I do under the root that came up in a problem before? I can do this right away.
The negative 4 times 154
What's going to happen when we do a negative 4 times a negative 154?
plus.
So I'll just cross it out, make it plus right away. All right, so we've got 15 plus or minus. Now, to me, that seems a little weird, right? Plus or minus means there's two answers. Does that mean that the width could be two different widths, this box? Let's see what happens. So we've got 154 times 4 plus 225. So it's the square root of 841 divided by 2. And now I want to actually get a decimal. So we could have square root of 841 plus 15 divided by 2. That means the width could be 22 inches. Now let's check the other number. Square root of 841 is 29. So 15 minus 29 divided by 2. Or the width could be negative 7. Which one of those is right? 22 or negative 7? Why? You can't have a negative width. Okay, so really the negative answer doesn't make any sense. So that's the width. What about the length? The length equals double the width. So if the width is 22, my length is 44. Okay, so kind of a confusing problem if you if you don't break it down, but if you start with the formula for the volume of a rectangular prism, and then work from there step by step, it works out to nice answers. That's it. Okay, any questions on that? Okay, so that's solving linear equations and then quadratic equations. A couple different ways, factoring or completing the square. Factoring or quadratic formula. So page 89, 35 to 39, that's really one big question. It's a break-even problem. So I think it's like find a formula for cost, find a formula for revenue, graph them, tell me where they cost. So that's 35 to 39. And then page 96 is what we just did on solving linear and quadratic equations. All right, so we'll take a look at that tomorrow. Tomorrow we should be on track to get done section 2.4, and then Wednesday I think we'll finish chapter 2.